Hi guys, it's Mrs. Webb here. I'm coming to you today to talk about graphing and curve straightening since we're starting our physics unit. So I guess the first thing to, chat about is to discuss, why graphing? What's the importance of graphing? Because truthfully, from my experience with students, typically graphing is just some horrible activity that teachers make you do for no apparent reason or rhyme or purpose or anything like that, right? But in physics, there really is a fundamental reason that we do graph, and primarily when we look at a graph, the number one thing is that it allows us to very quickly visually analyze what is happening with our data, so that we can pick out a trend, right, or a pattern. So it allows us to organize all of that data. It's much easier to see how data is behaving when you look at it in a picture representation like a graph versus looking at it in a data table where you can just see all these numbers, but you may not necessarily be able to pick out what's happening with those numbers. So that's the main reason that we graph, is to see that relationship, that trend in your data. But more importantly, when we talk about physics, the reason that we graph is because a lot of times we can actually get a mathematical representation. We can pull that out of the formula, and a lot of the physics equations that we use, and that we will be using in the kinematics unit, those all come from analyzing graphical data, right? And looking at trends of data. The other thing that we can do with graphs as well, and you guys have already had some experience with this, is that if we have a linear relationship to our graph, we can extrapolate and we can interpolate that data, right? And we can make predictions about what may happen in, further along in our data collection in the future, right? So we can make a lot of predictions about what we believe should happen if this particular trend continues. And this is something that you guys have also been seeing a lot in the news, because it seems like every day you open the news, COVID news is front and center for you guys, and there's always some graphical representation there that is projecting what should happen to our COVID numbers, right, over time if this particular trend continues. Right, so it's one of those things that in science becomes very, very important for analysis purposes, and it's important for you guys to be able to competently put together a graph and analyze that graph. So we're going to go over just a few things that should be second nature to you guys by now, because we have actually talked about them in the chemistry unit as well. But I've got two examples for you here in the notes. This first example here, right, we've got the number of veggies eaten. That's the manipulated variable there, and your lucky number up here. And it seems like two very, very interesting axes labels here, and as you can see, there appears to be absolutely no relationship between the number of veggies eaten and your lucky number. There's way too much scatter in this data to be able to say that there's any sort of a relationship, right? So this particular graph wouldn't really help us very much. We'd probably go back to our lab, and we would have to figure out a better way to analyze this particular set of variables, right? Something that works a little bit better, and this is something you guys have seen in the lab as well, but something that works a little bit better here is, for example, if we use our distance in kilometers as our manipulated variable, and we look at, well, what is the cost, maybe the cost of our fuel We're going on a road trip. We need to figure out what's the cost for our fuel. And if we're manipulating that distance, our cost is what's going to be responding, because the further we drive, the more money we're going to have to put in toward gas, right? So always your manipulated is going to be on your x-axis, your responding variable is going to be on your y-axis. Now we've plotted our data here. Notice that we're using nice numbers, right? So 1.0, 2.0, 3.0, 4.0 on the x-axis. We're using 4. Oh gosh, I don't know what axes I was using here. Don't pay attention to these axes. I think we're these ones. I would say this is not a good set of axes here because it doesn't half nicely. So yes, our 10 is here, but sheesh, minor increments with like 3 spacing doesn't go in nicely with 10. So I would not recommend this set of data up here. But we graph our data and we plot the data. We realize that, oh, lo and behold, if we look at this set of data that we've just plotted, this is a linear relationship here, right? We can actually physically put a ruler on top of this set of data, and we can pretty much approximate all of these data points. We're not connecting the dots. We're putting our line of best fit here. And if you notice here, there is a little bit of space between the origin and where that y-intercept is. So generally when we're collecting data, what that tells us is that in our data collection, very likely we have some error that has been accumulated throughout the data collection, right? And that is something that we would talk about in our conclusion down the road. Now, when we do our analysis of this, the first thing that we have to remember is we have to remember our equation for a straight line. And that equation for a straight line is our y equals mx plus b, right? Because we do have a straight line here. The m variable here is our slope. And so another thing that we have to remember is that our slope is our rise over our run. So our rise is our responding, our run is our manipulated. And in this case, if we were calculating slope, we would be looking at the change in our cost over our change in our distance, right? And when we choose data points to analyze here, we're not going to choose specific data points per se, because the data points themselves, they may lie on the line of best fit, but they may not. So what we're actually looking for is we're looking for these major axes that I've dashed in here. So there's one major grid line, here's another one, here's another one, here's another one. I'm looking for where this line of best fit crosses these axes. So I've got a cross there and there. I've got a cross almost there and there. That's what I'm looking for when I'm calculating my slope. I'll give you a better example down the road. So for our second point, this point here happens at the 4.00 and the 13 mark. This point here happens at the 1.0 and the 4.0 mark. And so for our slope, what we're going to do is we're going to take C2 minus, and I'm just going to fill this in here because it's gotten cut off. C2 minus C1 over D2 minus D1. Okay, we put in our C2, $13 minus $4 over 4 kilometers minus 1 kilometer, and we get that per kilometer we are going to be spending $2.25 per kilometer. Now, significant digits do matter here. So because this is only to one significant digit here, then our final answer would be $2 per kilometer is what we would expect to be spending on this particular road trip. Okay, so that's just a quick little example for graphing and kind of what we can do in terms of analyzing this graph. Now, because we're moving into physics, there's a couple of things that we need to make sure we're good with. The first thing is that graphs have a very, very, very specific format for their title. And the title always goes y as a function of x for, and then we explain whatever it is that we're collecting data for. The y is your responding. The x is your manipulated. So if we look at that previous example again, we were comparing cost as a function of distance for a trip to the store. In this case, cost is a function of distance for a trip to the store. That is a typical Physics 20 and Physics 30 graph title that you would use. Okay, in terms of labeling your axes, this is another thing that you must include. We're going to practice this when we meet together. You'll always include the variable, the symbol, and the units. So if I was going to label my distance for this particular graph on the x-axis, it's my manipulated, I would want to have that distance labeled in terms of distance, comma, the variable lowercase d, and in brackets, kilometers, because that's my unit for this particular one. Okay. So that's the format that you have to use for all of your graphs. A couple of reminders. When choosing a scale, they have to increase in equal intervals, so something like 2, 4, 6, 25, 50, 75. They have to half nicely. So choose increments that half easily so that you minimize error in plotting. Okay, so a good example for that is if we go back to my graph up here. Yeah, this is a nice increment. 10, 20 is definitely following the rules. It's a nice increment, but oh man, do these numbers not half nicely, right? Because I left 3 ticks before the 10, right? And 3 doesn't go nicely into 10. So you've got to choose something that works really nice with the minor increments on your graph and that you can half really simply. Okay. Usually with graphing scales, my general rule of thumb is, the KISS method. Keep it simple, stupid. So you shouldn't spend more than, I would say, more than 5 minutes. I would say even maybe more than 3 minutes trying to figure out what your axes spacing should be. It should be quick and it should be simple because it's something that you need to be able to read quick and simple. You shouldn't have a calculator out trying to, divide minor increments into your major increment. You need to do it quick and simply. So usually the easier the increment, the better. The other thing as well is that all of your graphs will start at the origin, at the 0, 0. And very, very, very important is that you do not use this compressed set of increments that you'll see used frequently in math. Don't use that zigzag where you collapse a bunch of numbers and then you start plotting, later on. So that's the other thing. Third thing is make sure that your graph fills the graph paper. So I don't want to see teeny tiny little graphs. Make sure that it fills the graph paper. And if my graph is something like this, like I've got a sheet of paper and they've given me a grid like this, okay, on this particular sheet of paper, I'm going to use the outer edges, outermost left edge and the outermost bottom edge. That's going to be my X and my Y axes. I'm not going to start my graph somewhere, in the middle of the paper. I'm going to use that border of my graph paper in order to create the X and the Y axes. And when I label it, I'm going to put a tick to show where those numbers are what axes those numbers are representing. The other thing, you must use graph paper, and your data must fit into the square sheet of graph paper. You can't draw lines beyond the graph paper because that'll create error. So that's just some refreshers on graphing. You guys have done a lot of graphing with me already, so I'm not too concerned. What we're going to do now, though, is we're going to do something which probably is going to be new for you guys, but what we're going to do, and we do a lot in physics 20 for sure, is we do something called curve straightening. And curve straightening is something that we do when we get a set of data that has a trend that doesn't give us a linear relationship right off the bat. And the reason is that what we generally want to do with graphs is we want to be able to interpolate data. We want to be able to figure out down the road, you know, what am I expecting my data to do? And that's a very hard thing to do when your trend is a curved line, because there is a lot of discrepancy as to where, once that data stops, where are you going to continue drawing your line? And so whenever you do sort of any sort of extrapolation or interpolation of data, you always want to do it with a linear line. You want to put a ruler on there, because if you have a ruler on there, there's no guesstimating as to where that ruled line is going to continue. So there's 4 relationships that you guys have to know in physics, and that you will work with more than you could possibly imagine in physics. The first relationship you guys have already seen, that's our direct or our linear relationship. And that's where we get, a straight line relationship where the y variable is directly proportional to the x variable. And we chatted in class about this proportionality statement. So for a direct or a linear relationship, our proportionality statement is y is proportional to x. And what that tells us in terms of our slope is that you're basically going to have y is proportional to x, right, in your slope here. So you've got y equals mx plus b. Versus if you have something like a power or an exponential relationship. In a power relationship or an exponential relationship, it's not a linear function, because what happens is as you start plotting your data, you start noticing that there's a very distinct curve in the trend of that data, and it curls, right? It starts with a very shallow slope, and that slope gets steeper and steeper as you move further along that x-axis. And so the relationship for this, the proportionality statement for this power or exponential relationship, is y is proportional to x squared. Okay, that's the relationship for this type of a graph. And if we look at that in terms of our slope, and we look at that in terms of our line of our equation of a line, we get that y is equal to m x squared plus b, right? So this is where the y is proportional to x squared comes into play. The third relationship that we'll look at is a root relationship. And in a root relationship, it's also a curved line. The difference being that instead of it curving upwards like it did in our power or our exponential relationship, our root relationship starts with a very steep slope. And as we move further along our x-axis, that slope gets less steep, and it kind of flattens out on us. And the relationship or the proportionality statement that we arrive at when that happens is y is proportional to the square root of x. And if we translate this over to our equation of the line, this is the same as saying y is equal to m times the square root of x plus b. The fourth relationship that we'll look at, and I believe actually we already looked at this when we looked at Boyle's law in the gas unit, is our inverse relationship. And that typically is going to be a curved line once again that starts rather steep, and as we move further along our x-axis, it shallows out. Okay, but you'll notice that the curve is in a different direction than in this root relationship. So the root relationship also starts steep and it flattens out, but it has a positive slope the whole way along, whereas your inverse relationship has a negative slope. And for this particular relationship, our proportionality statement is y is proportional to 1 over x. And so what that means in terms of our line, our equation of the line, is that the equation of the line becomes y is equal to m times 1 over x plus b. Okay. Now, where this is going to become important for us is that we're going to do a lot of work in terms of curve straightening. And so when we have data like this that gives us a curved trend, what we need to do is we need to manipulate the variables that we've collected for our manipulated variable, our x-axis, and we need to manipulate them in terms of what our proportionality statement is telling us this data is doing. So if our x data has a proportionality statement of y is equal to x, or is proportional to x squared, what we're going to do when we manipulate that data is we're going to look at all of that x data, all of the manipulated data, and we're going to square each of those values. And then we're going to replot that particular curve. If our proportionality statement is square root of x, then we'll take all of our x data, all of our manipulated data, and we're going to take the square root of each and every one of those data points, and then we'll replot it. If we've got an inverse relationship, we'll take each of our manipulated pieces of data, we'll do the inverse for each of those, and we'll get a brand new set of x values, and we'll replot them. And what you'll notice is that by manipulating that x-axis, what you do is you straighten your curved line, and you straighten it so that it ends up looking like a direct relationship. And now we can extrapolate. Now we can make predictions about what will happen in the future. So there's a few rules that you need to follow that I've written for you guys in the notes. First, you have to graph your raw data. Okay, graph your raw data collected. And that raw data is data that you haven't done any sort of calculations with, you haven't messed around with. It's the data that was collected in the lab. From your list, you're going to graph your data, You're going to have a look at the trend of your graph, and you're going to see what type of a trend does this give us. It has to be one of those 4 trends that we listed. So it'll either be a linear relation or a direct relationship, it'll be an exponential relationship, it'll be an inverse relationship, or it'll be a power relationship. So you have to determine what's the relationship for this particular graph. Once you've determined what the relationship is, now you can figure out, well, what's the proportionality statement for this particular graph? So if we have our power relationship, we know that our proportionality statement for this is y is proportional to x squared. Okay, this tells us how we will manipulate our x data. Step 4 is we're going to take our manipulate the x data, leave the y data untouched, and by manipulating the x data, since we know that the relationship for this example is y is proportional to x squared, we're going to square every single data point that we have in the x column. After we've manipulated that, we've got our brand new data table. We're going to graph this new data, and this should give us a straight line. So I've got this graph right here. I've got distance as a function of time. So we took an object, we had a stopwatch, we measured our time in seconds, And what we were doing was we were seeing, well, as every second goes on, how far has our particular object moved? Okay, what's the distance that that particular object has traveled? So we start at time 0, and the object is at 0 meters. We start the object moving. We start our clock. At 1 second, we measure that our object is at 0.4 meters. At 2 seconds, it's at 2.1 meters. At 3 seconds, it's at 4.6 meters. At 4 seconds, it's at 8.2 meters. At 5 seconds, it's at 12.7. At 6 seconds, it's at 18.1. At 7, it's at 24.2. So this object could be something like you have a ball at the top of a small ramp. You let go of the ball and you're watching every second how far has the ball descended down this ramp. Okay, and I plot this. So here's my my graph paper here. I've chosen, because I'm going up by 1 second intervals, I'm just going to use my time is 1 second. So I leave 2 ticks, have 1 second, 2 second, 3 second, 4 second, 5 second, 6 second, 7 second. And you'll notice that this does half nicely. So I've got, there's my half, which is 0.5. Half of that is 0.25. And then it makes it in here a bit easier to guess, you know, where would the 1 and all that kind of stuff be. For the next one, it's a little bit more challenging to pick out your axes, but I know I'm going from 0 to 24. So I've chosen it going up in increments of 2. And I've said every tick is going to be a 2. So I've got 2, 4, 6, 8, 10, 12, 14, 16, all the way up to 26. Okay. And this is also easy to half, right? The halfway point is my 1. Half of that is 0.5. It's nice and easy to half. You can read it really quickly. And I've plotted all of my data points. So let me just use a thicker line here just to show the data here. So I got 1 point here, 1 point here, 1 point there, 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 and there. And you can see my first point, I forgot to put in for you, my first point is my 0, 0. You can see that I can't put a ruler on here and make that ruler approximate all my data points. Because if I do put a ruler, it'll approximate a few points, but then the line just it moves away from my ruler. So I have to put a curved line on that approximates all these data points. Now, this particular graph, I need to figure out what is the relationship. So we can go back to our, group of relationships up here, and we'll see that it is a power or an exponential relationship. And so I know that means my proportionality statement is y is proportional to x squared. Okay. So I've got distance as a function of time, and I could say for a ball rolling down an incline, maybe. I've written my proportionality statement. I know that in this case, my distance is proportional to my time squared. Okay. That's my proportionality statement. And look at my axes. I've got distance, d in meters, time, t in seconds. So I'm actually going to come over here and I'm going to show you, actually I'll do it down here. What I want to do now is I want to straighten this curve. Okay, so I want to move my data so that it straightens out that sag in my curve, because if I do that, I can actually start to make some predictions about what might happen after that 7-second mark. So what I need to do with my data is, if I know that the proportionality statement is that distance is proportional to time squared, I'm going to manipulate this data here, my time data, by squaring each and every one of these values. So this would be my table 1. Okay, so now this is my observation. Now I would move into my analysis portion, and my table's gotten cut here. But I would come here and I would say, well, now to analyze this, I'm going to change my x-axis or my manipulated data so that I square each of those data points. So if I square 0, I get 0. If I square 1, I get 1. If I square 2, I get 4. I square 3, I get 9, right? I'm going to do that for all of them. So I've got 0, 1, 4, 9, and I continue going. Okay, and I'm actually going to do this for you. I don't have it done in the notes, but we're actually going to do this right now. So I've got 4, where did I go? 4 squared, which is 16. 5 squared, which is 25. 6 squared, which is 36. And 7 squared, which is 49 seconds. And let's see what our data points were. 8.2, 12.7. And then I have 18.1 and 24.2, I believe. 24.2. Okay, perfect. So now what we've got to do is we've got to take this data and we're going to graph our brand new set of data. I'm going to keep my axes for the y-axis consistent. Oops, I didn't mean to do that. So let's just move down so I got a little bit of room to groove here. Hopefully I gave myself enough space there. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Look at that, beautiful. And then here's my 0. This is distance D in meters. I'll move this down. My x-axis now has changed. Now I'm plotting time squared. So I'm not plotting time anymore. I'm plotting time squared, which is t squared. And that has a unit of seconds squared. Okay, so I have to change that x-axis. Now what I'm going to do is I'm going to look at what is my spacing here. I'm going from 0 to 49. Okay, so basically 0 to 50. And so I want to choose some increments that are nice to work with. Let's see, 10, 20, 30, 40, 50. That works pretty well. So we could say this is 10, 0, 20, 0, and 20, 30, 0, 40, 0, 50, 0. And you know what? Because I've still got axes, I'm going to continue labeling until I run out of space. So I can keep going up until 70.0. And now we're going to plot this data. So I'm just going to make this slightly smaller so I can see the data up above here. We know that our zero seconds, or seconds squared, is our 0 distance. That's kind of a thick line. Let's choose a smaller one. At 1, I have 0.4. So 1 will be, I'm going to undo that 1 dot. It's just slightly too big. There we go. There we go. So there's my point. Stop that. Okay, there's my 1 point. My 1 is going to be, gosh, ever so slightly over. So not very, very far from that first point. Good grief. This is being very finicky. Okay, somewhere around there. Like I said, it's a pretty thick dot. Let's move back up and see what my next point is. 4.0 and 2.1. So 4.0 is right about there. And then 2.1 will be about here. So probably around there. And then 9 and 4.6. So 9 is right just beside the line. 4.6 is about a quarter of the way up there, because the 5 is the halfway point. 16 and 8.2. So there's 15, 16, and 8.2. And then 25 and 12.7. So 25 is right on that line, and 12.7 will be right around the quarter mark as well. 36 and 18.1. So 36 is just slightly off of that middle line, and 18.1 will be just slightly off of the 18 axes, and then 49 and 24.2. So you can see, guys, as we plotted this data, notice that I regenerated that x-axis. As we plotted this data, now I can take a line, I can start it here, right? Oh, that's a really thick line. Let's undo that one. I don't want it to be quite so thick. Let's do just a thin blue line. So now I can take my line and I can draw that on top of all these data points, and you can see that from that original graph. Let's bring that original graph up. You can see that that curve that was originally on my data, that curve has actually gotten straightened out by manipulating the x-axis, by squaring all of those data points and replotting them. Okay, and now if I wanted to do something like solving for slope of this line, now I could actually do that, right? I could solve for the slope of this line. And what I would want to do if I solve for the slope of the line is I don't really care to use my red data points. What I want to do is I want to look at my grid lines, and I want to see where is a spot where my line of best fit is intersecting these grid lines. So obviously the 0, 0 is a spot. And if I keep following this line up, I notice that this point right here at the 20 and the 10, that intersects two grid lines really fairly nicely. If I keep moving up, this 40 and 20 intersects quite nicely, and that's probably the last one. And so if I was going to find my slope, what I would want to do is I would want to take 2 points, or a point here that crosses, and it's important that you draw this in so that you know what the points are that are being used for slope. And the reason I choose intersecting grid lines is because on those intersecting grid lines, there's no guesstimating as to what the numbers are on those grid lines. So here, I know that my 40.0 is my x, and my 20 is my y. For sure, there's no guesstimating. I know that here, it's my 0, 0. Okay, and there's no guessing as to, well, is that like a 40.1 or a 40.2? I want to minimize the amount of guessing when I'm calculating my slope. And so now for my slope, I know that's my rise over my run. And in this case, it's my change in my distance over my change in my time squared. And so that's going to be distance 2 minus distance 1 over my time squared 2 minus my time squared 1. Right, and I'm going to put my numbers in. So my distance 2 is my 20 meters. I don't need brackets there. My 20 meters minus my 0 meters. I don't know why I'm putting brackets. Divided by my 40.0 seconds squared minus my 0 meters per second squared. Right? And this is the same as 20 meters divided by 40.0 seconds squared. The other thing to note is that in math, a lot of times we'll leave this as a fraction. In physics, you must take it to a final number, just a single number. And so this is the same as saying 0.50 meters per second squared. Okay. Significant digits, there's 22 significant digits, so that's why I put this to 50. The other thing is look at your units, right? The units in the slope are going to tell you something very important about what you're solving for. Okay, and we'll get into that more when we get into our kinematics unit. But for now, what we're going to do is we're going to practice manipulating data and curve straightening, because you guys are going to do that in your first pendulum lab this week. So guys, I'm going to leave you on that note, and I hope you guys are doing well. If there's any questions, please let me know the next time we meet. And yeah, we're going to get our physics on. Take care.